Oxidation and reduction. So what is really happening during these oxidation and reduction reactions that causes iron to rust and enables the process of photosynthesis to take place in plants? Oxidation and reduction is the process by which substances gain or lose electrons. This process is commonly known as redox, which is short for reduction oxidation. In a redox reaction, two events must happen. One element must gain electrons and one element must lose electrons. Thus, the key characteristic of a redox reaction is the exchange of electrons. Reduction is the gain of electrons and oxidation is the loss of electrons. One way to remember what happens in a redox reaction is to use this mnemonic device. Leo the lion says, grr. Loss of electron is oxidation. Gain of electron is reduction. Reactants and products. Just as with other types of chemical reactions that you have learned about, in oxidation-reduction reactions, there are reactants and products. Prior to the reaction, the substances are called reactants. After the reaction, they are called products. One way to think of this is with a baking example. The dough for a loaf of bread contains the reactants sugar, flour, butter, and so on. After the reaction, baking, the product is the loaf of bread. In a reduction-oxidation reaction, you begin with reactants and end with products. The following screen contains a short video that illustrates a reaction involving lead bromide. In this reaction, lead bromide, the reactant, is heated. Can you predict what the products of the reaction will be at the end? Watch this video about the process of electrolysis, featuring an example of an oxidation-reduction reaction involving lead bromide. Once you are done, click Next to answer a question based on what you observed in the video.
The Earth's crust contains many compounds, but the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide. Split the aluminium from the oxygen, and you have one of the world's most useful metals. You can split a compound using electricity.
Lead bromide oxidation-reduction reaction. Let's take a closer look at the lead bromide oxidation-reduction reaction. PbBr2 yields Pb plus Br2. We can break oxidation-reduction reactions into two half reactions, the oxidation reaction and the reduction reaction. Here's the oxidation reaction. 2Br minus yields Br2 plus 2E minus. The bromide ions lose 2 electrons. Now, take a look at the reduction reaction. Pb2 plus 2E minus yields Pb. The lead ions gain 2 electrons. Together, these two half reactions form the oxidation-reduction reaction. The bromide ions lose electrons and the lead ions gain electrons. Electrons are exchanged, which is the key characteristic of an oxidation-reduction reaction. Calculating oxidation numbers. To determine whether a substance is being oxidized, losing electrons, or reduced, gaining electrons, in a redox reaction, you need to calculate the oxidation numbers for the elements in the reaction. Oxidation numbers describe the electrical state of atoms. They are the sum of the positive and negative charges in an atom, which show how many electrons are gained or lost by an element when atoms turn into ions. When first learning the rules for oxidation numbers, it is helpful to have a chart listing all the rules. Some periodic tables list the oxidation states for elements and can also be used as a helpful reference. With enough exposure, you'll most likely memorize some of the rules. Let's take a look at the rules on the next page. Once you have reviewed the rules, move on in the lesson.
So let's take a look at the rules. For neutral compounds, the sum of the oxidation numbers equals 0. Neutral, 0. The sum is 0. So NaCl, the Na is positive 1 charge, Cl is negative 1 charge. Together, they are neutral, sum equals 0. Okay, group 1 metals except hydrogen, +1. Lithium +1, sodium +1, potassium +1. Group 2 metals plus 2. Be plus 2, Mg plus 2. Oxygen in compounds most of the time is negative 2. So in the NO2, the O oxygen is negative 2. Hydrogen in a compound most of the time is positive 1. But if in the compound with metals, it's negative 1. So H2O, the H is plus 1. NaH, the H is negative 1. Fluorine in compounds is negative 1 charged. F in lithium fluoride, F is negative 1. And as we know, the one on the right side is negative charge normally. For monoatomic ion, the oxidation number is equal to the ion's charge. So Fe 3 plus must be positive 3 charge. Br 1 minus must be negative 1 charge. For polyatomic ions, the sum of the atomic oxidation numbers equal the ion's charge. So SO3 2 minus, that means together is negative 2 charge. And then because O is negative 2 charge, and then negative 2 times 3, that give you negative 6. But this is not correct. Then S should be plus 4 charge. Otherwise, how could you have the SO3 become negative 2 charge?
Oxidation state versus formal charge. How do you calculate them? For oxidation state, you need to know which elements are more electronegative. So oxygen's more electronegative than hydrogen. All the bonds with oxygen and hydrogen, count them as being on the oxygen, which means the oxygen has 8 electrons and oxygen normally has 6. So that means the oxidation state of the oxygen is negative 2. The hydrogens normally have 1, but in this scheme they have 0. So they're 1 short, so it means they're positive 1. Those are the oxidation states. If you want to know the formal charge, you cut the bonds in half. You count like this. So this way the oxygen has 6, which is what it's supposed to have. So it has a formal charge of 0. And the hydrogen also has a formal charge of 0 because the hydrogen has its 1 electron. Methane. Carbon is more electronegative than hydrogen. So all of these count as being on the carbon, which puts carbon at 8. Carbon normally is 4, which means that the carbon's actually at negative 4 oxidation state. Each hydrogen is missing its 1, and so it's at positive 1 oxidation state. And then again, if you cut the bonds in half, the carbon is counted as having 4, which is its usual, so formal charge of 0. And the hydrogen gets its 1, which is as usual, so it has a formal charge of 0. Finally, carbon monoxide. Oxygen is more electronegative. So if you count like this, the oxygen has 8, and its oxidation state is negative 2. But if you cut the bonds in half, the oxygen has 5. It's supposed to have 6. So the oxygen is actually at plus 1. Likewise, the carbon is at positive 2 oxidation state. And the carbon has 5 when it's supposed to have 4, so the carbon's actually at negative 1.
In this video, we'll calculate the formal charge for each element in SO3 2-. This is called the sulfite ion. So we start with the Lewis structure, and what formal charges are going to tell us is whether this is the best or most likely Lewis structure for SO3 2-. Let's just do the sulfur here in the center. So sulfur, that's in group 16, sometimes called 6A. So just sulfur is going to have 6 valence electrons. Looking at our Lewis structure, we're going to look at unbonded electrons. Sulfur has 2 electrons that aren't involved in chemical bonds. They're not between atoms. So we have 2 of those, and then 1/2 of the bonded electrons. These are bonds, and then we have a double bond. So we have 4, 6, 8. 8 over 2. So 6 minus 2 minus 4, that gives us a 0. So this sulfur in the center is going to have a formal charge of 0. And note, even though it has more than 8 valence electrons, that's okay. Sulfur is an exception. It can have an expanded octet. For the oxygen atoms, we have these two right here. They're identical. So let's just do one of these, the single bonded oxygen. So we'll put an oxygen here. Oxygen is in group 16 with sulfur. It has 6 valence electrons. Then we're looking at unbonded, 2, 4, 6. So 6 unbonded electrons. And then we'll subtract 1/2 of the bonded. There are only 2 here. This is a single bond, so 2 over 2. We end up with 6 minus 6. That gives us 0 minus 1. We have a -1 formal charge here for this oxygen. And since this is the same here, just a single bond, -1 as well. Let's do the oxygen with the double bond. Oxygen, that's going to be 6 because it's oxygen. And then we're looking unbonded, 2, 4. So 4 unbonded, and then the bonded, we have the double bond here. So 2, 4. So we have 4, but we divide that by 2. 6 minus 4 is 2, minus 2 is 0. So this oxygen has a formal charge of 0. So at this point, these 2 oxygens here, their formal charge is -1. But that makes sense because it's an ion. The total ionic charge is 2 minus. So we have 2 negative 1s. That equals this 2 minus here. So that makes sense. But everything else is as close to 0 as it can possibly be. We said the sulfur in the center, that was 0. That makes this the most likely or favorable Lewis structure for SO3 2 minus. This is Dr. B calculating the formal charge for each element here in SO3 2 minus.
Practice calculating oxidation numbers. Now that you are familiar with the rules for oxidation numbers, let's practice calculating oxidation numbers for a few elements and compounds, starting off with chromium trioxide, CrO3. Remember, you can refer to the periodic table and chart to help you practice calculating oxidation numbers. The first thing you'll notice is that CrO3 is a compound, so the oxidation numbers need to add up to 0. Oxygen has an oxidation number of -2 and contains 3 oxygen atoms for a total charge of -6. Therefore, to sum to 0, chromium needs to have an oxidation number of +6. We can write the oxidation numbers for the elements in the compounds like this: +6 minus 2 CrO3. Let's take a look at another example, sodium nitrate, NaNO3. NaNO3 is a compound, so the oxidation numbers need to add up to 0. Oxygen has an oxidation number of -2 and contains 3 atoms for a total charge of -6. Sodium is a group 1 metal, so it has an oxidation number of +1. Therefore, to sum to 0, nitrogen needs to have an oxidation number of +5. We can write the oxidation numbers for the elements in the compound like this: +1 plus 5 minus 2, NaNO3. Now, you will have a chance to apply what you have just learned by matching the correct oxidation number to its corresponding element. Oxidation numbers in redox reactions. Now that you know how to find the oxidation numbers for atoms in their elemental form and elements in compounds, let's look at finding oxidation numbers in redox reactions. As we discussed earlier, in an oxidation-reduction reaction, electrons are being transferred. 2 events must happen. One element must gain electrons, and one element must lose electrons. When these 2 events occur, the oxidation number of the elements changes. When electrons are lost, the oxidation number goes up. It becomes more positive. When electrons are gained, the oxidation number goes down. It becomes more negative. In a redox reaction, you need to examine the oxidation numbers to determine which element was oxidized and which element was reduced. When an element's oxidation number increases, it means that the element lost electrons and was oxidized. Conversely, when an element's oxidation number decreases, it means that the element gained electrons and was reduced. Let's take a look at an example of a redox reaction between calcium and oxygen and examine the oxidation numbers. 2Ca plus O2 yields 2CaO. The first step is to find the oxidation numbers of each substance before the reaction, calcium and oxygen, the reactants. From the chart, we know that for any element that is not part of a compound, its oxidation number is 0. So both calcium and oxygen have an oxidation number of 0. 0, 0. 2Ca plus O2 yields. The second step is to find the oxidation numbers of each substance after the reaction, calcium and oxygen and calcium oxide, the products. From the chart, we know that oxygen has an oxidation number of -2. Since the sum of the oxidation numbers for elements in a neutral compound must be 0, the oxidation number of calcium is +2. +2 - 2 yields 2CaO. Lastly, we compare the oxidation numbers for each substance to determine whether a loss or gain of electrons occurred. 0, 0, +2 - 2. 2Ca plus O2 yields 2CaO. Notice that calcium had an oxidation number of 0 before the reaction and an oxidation number of +2 after the reaction. Oxygen had an oxidation number of 0 before the reaction and an oxidation number of -2 after the reaction. Since calcium lost electrons and oxygen gained electrons, calcium was oxidized and oxygen was reduced. Now, let's look at an example of a redox reaction between magnesium and hydrogen chloride. 0 + 1 - 1, 0 + 2 - 1. Mg plus HCl yields H2 plus MgCl2. The oxidation number of magnesium before the reaction is 0, and the oxidation number of hydrogen before the reaction is +1. After the redox reaction, the oxidation number of magnesium is +2, and the oxidation number of hydrogen is 0. Note that the oxidation number for chlorine remained the same. Chlorine is considered a spectator ion in this reaction because its charge did not change. Since magnesium's oxidation number went up, became more positive, it was oxidized. Since hydrogen's oxidation number went down, became more negative, it was reduced. In redox reactions, an oxidizing agent and a reducing agent is always present. The oxidizing agent is the substance that is reduced. The reducing agent is the substance that is oxidized. In this example, magnesium is the reducing agent because it reduced hydrogen or gave electrons to hydrogen. Hydrogen is the oxidizing agent because it oxidized magnesium or gained electrons from magnesium.
Okay, step 1, find the oxidation number for the reactants. Find the oxidation number of the elements of the product. So because O2 is -2,
To find the oxidation number for each of the elements here in ZNO, zinc oxide, we have these rules here to guide us. Zinc oxide is a neutral compound. That's because it doesn't have a plus or a minus here. And in a neutral compound, all the oxidation numbers, they're going to add up to 0. So that's very helpful. We also know that oxygen, that's going to have a -2 oxidation number, except in a few cases. So -2, that's our oxygen there. Because everything has to add up to 0, if the oxygen, the one oxygen, is -2, the zinc will have to be +2.
Now the first rule that you need to know is that the oxidation state of any pure element is always 0. So the oxidation state of oxygen gas as a pure element is 0. Fluorine gas as a pure element is 0. Even phosphorus as a pure element is 0. So if there's no charges and it's only one pure element, it's not a compound, the oxidation state will always be 0. So that's the first rule you need to keep in mind. Now the second thing is the oxidation state of ions. The oxidation state of the zinc 2+ ion is basically the charge of what you see there. It's +2. The oxidation state of the Fe+3 ion is simply +3. Now sometimes you might have diatomic ions, for example, the mercury 2+ ion. Individually, each mercury ion has an oxidation state of 1 because there's 2 of them. So you need to write an equation. 2 mercury atoms has a net charge of +2. So if you divide both sides by 2, you can get the individual oxidation state of each mercury particle, which is +1. So here's another example. This is the peroxide ion. To find the oxidation state of each oxygen atom in this ion, you can write an equation as 2 oxygen atoms with a total charge of -2. So individually, each oxygen atom has a charge of -1. So that's the oxidation state of oxygen individually in the peroxide ion. This is the superoxide ion. So if you want to find the oxidation state, you need to divide the total charge by 2. So each oxygen atom has a net charge of -1/2. So two of them combined will have a net charge of -1. So keep this in mind. Anytime you have a pure element, the oxidation state will always be 0. And if you have an ion, let's say if it's a monatomic ion, the oxidation state is the same as that ion. Now let's talk about compounds. Whenever you have fluorine inside a compound, when it's not a pure element, fluorine is always going to have a -1 oxidation state. Fluorine is the most electronegative element. When oxygen is in a compound, it's going to have a -2 oxidation state, unless it's bonded to fluorine, or unless you hear the name peroxide or superoxide. Whenever you hear the name peroxide, oxygen has a -1 oxidation state. If you hear the word superoxide, it has a -1/2 oxidation state. But if you hear the word oxide, then the oxidation state is -2, which is 99% of the time. Now, hydrogen will have an oxidation state of +1 when bonded to a nonmetal. When bonded to a metal, hydrogen will have an oxidation state of -1. And really, the key is electronegativity. Hydrogen is more electronegative than most metals. That's why it bears a negative charge. But hydrogen is usually less electronegative than most nonmetals. And so that's why it bears a positive charge. So typically, the element that's more electronegative is the one that usually carries the negative charge. Now let's work on some examples. What is the oxidation state of magnesium and chlorine in this compound? By the way, most halogens are usually -1. Chlorine typically has a -1 charge, like fluorine. If we write an equation, Mg plus 2Cl, this whole compound is neutral, so therefore the total charge is 0. Now, if chlorine has a -1 oxidation state, that means magnesium has to have a +2 oxidation state. You can literally solve it. And it makes sense. Magnesium is an alkaline earth metal, which typically has a +2 charge. Go ahead and find the oxidation states of aluminum and fluorine in this example. Well, we know that fluorine is -1 in a compound, always. And aluminum, based on where it's located in the periodic table, it's typically +3 within an ionic compound. And you could solve it too. Al plus 3F should add up to 0, because the net charge is 0. So each fluorine atom has an oxidation state of -1. So now we got to add 3 to both sides. So aluminum has an oxidation state of +3. Here's another example. Find the oxidation state of vanadium and oxygen in this compound. So this is called vanadium oxide. So whenever you hear the word oxide, oxygen has a -2 charge. So we got 2 vanadium atoms plus 5 oxygen atoms with a net charge of 0. So each oxygen atom has an oxidation state of -2. 5 times -2 is -10. And then add 10 to both sides, so 2V is equal to 10. Next, divide both sides by 2. So 10 divided by 2 is 5. And so the oxidation state of vanadium is +5. Now let's go over some examples containing polyatomic ions. Consider sulfate. What is the oxidation state of sulfur in sulfate? Well, we know oxygen is usually -2. So let's write an equation. Sulfur plus 4 oxygen atoms has a net charge of -2. So each oxygen atom has an oxidation state of -2. And 4 times -2, that's -8. Next, we need to add 8 to both sides. -2 plus 8 is +6. So this is the oxidation state of sulfur in sulfate. Let's look at another example. Phosphate. Go ahead and find the oxidation state of phosphorus in phosphate. So once again, oxygen is still -2. So we got a phosphorus atom plus 4 oxygen atoms, and the net charge is -3, based on what we see here. So it's going to be P plus 4 times -2, and 4 times -2 is -8, and then add 8 to both sides. So -3 plus 8, that's going to be +5, and that's the oxidation state of phosphorus. Let's look at another example. Let's try nitrate, and also chlorate as perchlorate. Go ahead and find the oxidation state of nitrogen and chlorine in these 2 polyatomic ions. So we have a nitrogen, 3 oxygen atoms, and that's going to equal a net charge of -1. So O is -2. 3 times -2 is going to be -6. And -1 plus 6, if we add 6 to both sides, that's going to be +5. So that's the oxidation state of nitrogen. And for chlorine, in perchlorate, it's going to be Cl plus 4 oxygens equals a net charge of -1. So this is going to be 4 times -2, which is -8. And then -1 plus 8, that's going to give us an oxidation state of +7. So now you know how to find the oxidation states of elements within compounds and polyatomic ions. Now, I want you to understand the concept of electronegativity and how it relates to oxidation numbers. Electronegativity increases towards fluorine on a periodic table. So as you go up and to the right, the electronegativity increases. So let me give you some values of common elements. So let's say hydrogen is somewhere in the corner over there, and then we have boron, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, phosphorus, and sulfur. Hydrogen has an electronegativity value of 2.1. For boron, it's 2.0, carbon is 2.5, and then 3.0, 3.5. Fluorine's the highest, it's 4.0. Phosphorus, it's 2.1, it's the same as hydrogen. Sulfur is 2.5, chlorine is 3.0, and this is 2.8, iodine is 2.5. So keep these values in mind. So here's a question for you. What is the oxidation state of oxygen and fluorine in oxygen difluoride? Now, oxygen has an electronegativity value of 3.5. Fluorine is 4.0. So which one is more electronegative? Electronegativity is the ability of an atom to attract electrons to itself. So fluorine is going to pull on electrons in its molecule. It's going to have a stronger pull than oxygen. So fluorine is going to acquire a partial negative charge, whereas oxygen is therefore going to acquire a partial positive charge because fluorine pulls on the electrons stronger than oxygen can. So in this example, oxygen will not have its typical charge of -2. The only time oxygen will have its oxidation state of -2 is if it's the most electronegative element in that compound. If it's not, then it's going to have a positive oxidation state. Keep in mind, anytime fluorine is in a compound, it has an oxidation state of -1. And the reason for that is because fluorine is the most electronegative element on a periodic table. So now we can solve for oxygen. So O plus 2F should have a net charge of 0 because there's no number here. So fluorine is -1. 2 times -1 is -2. So if we add 2 to both sides, oxygen is going to equal +2, which makes sense because it's partially positive in this particular example. Now let's look at 2 other examples, hydrochloric acid and sodium hydride. Chlorine has an electronegativity value of 3.0. Hydrogen is 2.1. And sodium, it's like 1 point something. I'm not sure what the exact number is. It could be like 1.5, 1.7, but I know it's less than 2. So in this example, hydrogen bears a partial positive charge. Chlorine bears a negative charge because chlorine is more electronegative than hydrogen. So therefore, chlorine is going to have its oxidation state of -1, which is typical of most halogens. Hydrogen is going to have an oxidation state of +1. As you mentioned before, whenever hydrogen is bonded to a nonmetal, the oxidation state is usually +1. Now what about in sodium hydride? Well, we know that sodium is an alkali metal, which always have a +1 charge. So therefore sodium is going to have an oxidation state of +1. But hydrogen has an oxidation state of -1. Typically, when hydrogen is bonded to a metal, it usually has a -1 oxidation state. And it makes sense because hydrogen is more electronegative than most metals. So it usually bears the partial negative charge. That's why it has a negative oxidation state. Sodium has the positive charge, so it has a positive oxidation state. And so you could use electronegativity to help you determine what the oxidation state will be. So let me give you another example. BH3. What is the oxidation state of boron and hydrogen? Feel free to try that one. Now hydrogen has an electronegativity value of 2.1 and boron is 2.0. Now is boron a metal or non-metal? In this example, hydrogen is more electronegative. So hydrogen bears the partial negative charge, or boron bears the partial positive charge. So therefore hydrogen is going to have its oxidation state of -1 because it's more electronegative than boron. So then this is going to be B plus 3H, which is equal to 0. So 3 times -1 is -3. So boron is going to have an oxidation state of +3 in this example. Now let's consider these 2 examples. Sulfuric acid, or rather hydrosulfuric acid, and also sulfur dioxide. Now hydrogen has an EN value of 2.1. Sulfur is 2.5, and oxygen is 3.5. So in sulfur dioxide, oxygen has the partial negative charge, sulfur has the partial positive charge. Now in H2S, hydrogen has the partial positive charge, sulfur has the partial negative charge. Now in the periodic table, when you have elements like nitrogen, oxygen, fluorine, typically nitrogen has a -3 charge, oxygen -2, fluorine -1. Sulfur too. Sulfur usually has a -2 charge, if sulfur is the more electronegative element. So looking at H2S, hydrogen is bonded to a nonmetal that is more electronegative than itself. So hydrogen is going to have the +1 oxidation state. And there's 2 of them. So sulfur, in this example, has its normal oxidation state of -2. So you can base your answer on a periodic table if sulfur is the more electronegative element. Now in SO2, you can't do that because sulfur doesn't have the partial negative charge, so you can't base the charge on a periodic table. You can do so, however, for oxygen, because oxygen is the electronegative element in that compound. So you can use the -2 charge for oxygen. So oxygen is going to have an oxidation state of -2, and to find it for sulfur, it's going to be S plus 2 oxygen atoms equals 0. So that's 2 times negative 2, which is negative 4. So sulfur is going to have a positive oxidation state of 4 due to the positive partial charge. So elements that are less electronegative, typically those are the ones you got to solve for. The ones that are more electronegative, you can find a charge based on a periodic table if they carry a negative charge. Now let's look at some other examples. NH3 and NO2. Go ahead and find the oxidation state of each element. Now, in ammonia, hydrogen has an EN value of 2.1, but nitrogen is more electronegative, it's 3.0. So therefore, nitrogen should have its normal charge of negative 3. If we write an equation, N plus 3H is equal to 0, hydrogen is going to have a positive 1 charge. It's partially positive, whereas nitrogen is partially negative. So typically when hydrogen is bonded to a nonmetal, it's usually plus 1, which means N has to be negative 3. So as you can see, nitrogen is the electronegative element in this example, and it has its periodic charge of negative 3, which you can find in the periodic table. Now in this case, O is more electronegative, so nitrogen is going to have a different oxidation state. It's not going to be its natural oxidation state of negative 3. So in this example, it's going to be positive 4. So typically, when you have elements like nitrogen, sulfur, phosphorus, if they carry an element that's more electronegative than itself, those are the elements you got to solve for. The one that usually has a partial positive charge. Now try these two examples, methane and carbon dioxide. In methane, hydrogen has a positive 1 charge. Hydrogen is less electronegative than carbon, so it's going to be partially positive. Carbon is going to be partially negative. So solving for carbon, we have C plus 4H is equal to 0. So that's 4 times 1. So C is negative 4. So when carbon is bonded to hydrogen, carbon has a negative oxidation state. But when carbon is bonded to oxygen, it's going to have a positive oxidation state. When it's bonded to hydrogen, it has a negative oxidation state. So oxygen is negative 2, and there's 2 of them, so carbon's going to have to be positive 4 in this example. Now sometimes, you might have elements that have an average oxidation state that's not a whole number. Let's try these two, C3H8 and Fe3O4. In this example, hydrogen is less electronegative than carbon, so it's going to be positive 1. So if we write the formula 3C plus 8H is equal to 0. So that's going to be 8 times 1. And if we subtract 8 from both sides, 3C is equal to negative 8. So carbon, on average, has an oxidation state of negative 8 over 3. Now let's do the same thing for Fe3O4. So we got 3 iron atoms and 4 oxygen atoms with a net charge of 0. So oxygen has an oxidation state of negative 2. So 4 times negative 2, that's negative 8. And if we add 8 to both sides, we're going to get this. So Fe has an oxidation state of 8 over 3. So 8 over 3 is about 2.67. Now keep in mind, an individual iron atom cannot have a charge of 2.67. It's usually a whole number, like positive 2 or positive 3, because electrons and protons, they basically have numerical charges. An electron has a charge of negative 1, a proton has a charge of positive 1. So a typical ion won't have a decimal charge. So what does it mean that the average oxidation state is 2.67? So what is meant by that? In this compound, there are 3 iron ions and 4 oxygen ions. Each oxygen has a charge of negative 2. So the total negative charge is negative 8. In order for the compound to be electrically neutral, the total positive charge has to be positive 8. Iron metal has 2 common oxidation states, positive 2 and positive 3. Now they all can't be positive 3 because 3 plus 3 plus 3 is 9, and they can't all be positive 2 because 2 plus 2 plus 2 is 6. So some of them is positive 2 and some are positive 3. So the question is, how many iron ions have a plus 2 charge and how many have a plus 3 charge? In order to get up to 8, 2 of them has to have a positive 3 charge and 1 of them has to have a positive 2 charge. If you average the numbers 2, 3, and 3 and divide it by 3, that's going to be 8 over 3, which averages out to 2.67. So whenever you get a decimal value, what it really means is that that's the average oxidation state. Individually, some are positive 3 and some are positive 2. So the individual ions should have a numerical oxidation state. But when you have multiple of them, the average could be a decimal value because these, they don't all have to be the same. They can be different. So hopefully this makes sense in terms of why some oxidation states have a decimal value. Now let's try polyatomic ions that have 3 different elements in it. Go ahead and find the oxidation state of every element in that polyatomic ion. So oxygen has an oxidation state of negative 2. Hydrogen is positive 1 when it's bonded to nonmetals, usually. So all we got to do is find sulfur. So H plus S plus 3 oxygen atoms has a net charge of negative 1. So hydrogen is 1, oxygen is negative 2, and so 3 times negative 2, that's negative 6. And then 1 plus negative 6 is negative 5. So now let's add 5 to both sides. Negative 1 plus 5 is positive 4. So in this example, sulfur has an oxidation state of positive 4. Go ahead and try this one, K2CrO4. Find the oxidation state of every element in that example. So we have 2 potassium atoms, a chromium atom, and 4 oxygen atoms. Now we know oxygen is going to have an oxidation number of negative 2. Potassium is an alkali metal, which all of them have a positive 1 charge. Chromium is the transition metal, and it has a variable charge, so that's the one we got to solve for. So this is going to be 2 times 1 plus Cr plus 4 times negative 2, and all of that is equal to 0. So 4 times negative 2, that's negative 8, and 2 plus negative 8 is negative 6. So therefore, in this example, chromium has an oxidation state of positive 6. Try this one, potassium bicarbonate. Find the oxidation state of carbon in this example. So we know oxygen is going to be negative 2, potassium, an alkali metal, is plus 1, and hydrogen is actually bonded to the oxygen in bicarbonate, if you were to draw the Lewis structure. So therefore, hydrogen is bonded to a nonmetal through a covalent bond, and so it's going to be plus 1. So we have K plus H plus C plus 3O, and that's equal to 0. So K is positive 1, hydrogen is 1, and oxygen is going to be 3. Well, oxygen is negative 2, but we got to multiply that by 3. So 1 plus 1 is 2. 3 times negative 2 is negative 6. And then 2 plus negative 6, that's negative 4. So in this example, carbon is positive 4. Potassium bicarbonate, you could break it up into 2 ions, K plus and HCO3 minus. So just by looking at K plus, that tells you that K has an oxidation state of positive 1. Now, bicarbonate is basically the sum of the hydrogen ion and the carbonate ion. So therefore, you can see that hydrogen in this example also has a positive 1 charge. And then from this, you could find the oxidation state of carbon. You could say C plus 3O has a net charge of negative 2. And then you have to add 6 to both sides. So negative 2 plus 6 is positive 4. So if you understand the ions and all the polyatomic ions, you could break it down individually to see that hydrogen has a positive 1 charge in this example. And the same is true for K. So that's why it's good to know the polyatomic ion sheet. Now I have 2 more examples for you. BrCl3 and IBr5. Find the oxidation state of every element in this example. So most halogens, like fluorine, chlorine, bromine, iodine, they typically have a negative 1 charge. But both bromine and chlorine can't be negative. So which one is negative and which one is positive? Keep in mind, bromine has an electronegativity value of 2.8. Chlorine is 3.0. Iodine is 2.5. So in this example, chlorine bears the partial negative charge. Bromine is partially positive. So therefore, chlorine is going to have its natural oxidation state of negative 1. Bromine, we need to calculate it. So it's going to be Br plus 3Cl, and that's equal to 0. So this is going to be 3 times negative 1, and so we can see that bromine has an oxidation state of positive 3. Now, in the second example, bromine is going to carry the partial negative charge. Iodine carries the partial positive charge. If it's written correctly, usually the electropositive element is written first. The electronegative element is written second. So the one that you see on the right side is usually the one that carries the natural charge that can be found on the periodic table. So in this case, bromine is going to have its natural oxidation state of negative 1. So iodine is going to have an oxidation state of positive 5 in this example. So hopefully you understand the relationship between electronegativity and oxidation numbers. So that's it for this video. Thanks for watching and have a good day.